So today we're going to be looking at one of Lidl's new battery-powered devices. It is the cordless coffee machine that's come out sometime in the last month, available for about 35 euros. And as you will see in just a moment, so this is the machine itself. As you can see, we have a bit of a problem getting something this big into shot on the bench. So it comes with a couple of accessories and options. So you have the coffee pod adapter that you can put the flexible cloth bag coffee pods into, or it comes built in with your standard ground coffee capability that you can just fill into the little basket and stick in here for brewing. It also comes with one fairly stylish stainless steel coffee mug with a top to keep it warm at the build site, and the machine itself. So as we can see here, it opens up on the top. That reveals the water tank, 240 milliliters, so you're going to have to refill it a few times to make a couple of cups of coffee. And in the top lid is the loading spoon. So I've gone to the trouble to remove most of the screws out of the machine. So if we just take a quick look at the front, we can see that there's just one button for power, and on the rear we have the battery plug-in connector and this handy carrying handle. So I'll just lay it down flat like this. We can get a look at the general shape, and here we have the nameplate. And the machine is built up in parts, just like a Russian Matryoshka doll. So it actually disassembles, in this case from top to bottom. We can take the top plastic element off gingerly. There we go. That is carrying the cables just to the button and the LED. And we have our steam hose coming up to this top unit. And sort of interesting design element here, the nameplate of the manufacturer just slots into this front hole, right, something like that. So they actually make it very easy for other companies to brand it in their own name. So if we go to the next level, this should reveal the more interesting heating part. Oop, there it goes. So as you can see, this reveals the main functioning element, which is the boiler unit, the heater. So really the only connections we have going up to the top of the unit are our water inlet hose that comes through a one-way valve once you place the water tank on it, and the water just gravity feeds into this U-bend heater. And we have our coiled heater on this outside aluminum casting with the water tube going through the middle. And here we have the two contacts for the heater, the positive and negative, and we have our NTC thermistor that is bonded to the side of the heater here that goes out to this cable here. The white cable coming off the top is just plus and minus, or better say a ground, a input to the green LED, and an output from the switch. Here we have nice silicon cables going to the heater. This measures out at, let me just see here on my schematic, yep, 0.5 ohms on the heater. So if we're looking at around 20 volts in the battery, this heater is pulling ideally 42 amps, giving 880 watts approximately of heating power to the machine. As the manual states, the coffee machine can make 3 to 4 cups of coffee, so you're really taxing that battery every time you make a cuppa. So here I've unsoldered and disconnected all the cable work from the unit itself. And that really only leaves us with this bottom part where the PCB has decided to fall out of the mounting I had gingerly placed it into. So this just stands something like that, and then you can slide a battery onto there to power it. And the bottom of the machine is totally empty. This is just the bottom plate with a couple of rubber feet. And if we can find a marking here, it is marked PP, so made from the finest recycled Chinesium plastic bag polypropylene that is known to man. So here we have the control PCB nestled into the back of the coffee machine body, and usually it's held in there by 2 screws. We can just pull that out for demonstration purposes. And now we come to the PCB. Fairly simple design, positive and negative from the battery, then thermistor or digital communication input from the battery, and it only has these 2 plug-in spots, one's for the NTC thermistor, one's for the top side LED indicator and switch, and then we have these 2 contacts that I've desoldered through hole for the heater. So we'll be back in just a second looking at this board in detail. So here we are again after a quick change of scale. This is the PCB board I showed you in the coffee machine just a moment ago. So here we have our battery input with our 3 connections. Most of the back are just a couple of connection vias and a massive ground plane. And if we flip the board over on this side, we can see we have most of our functional components here. So we have the thermistor input going in here. We have our switch and LED indicator here. We have our heater inputs here. Then we have our MCU. We have 2 big MOSFETs obviously controlling the heater. And we can see we have quite the array of multiple SOT23 transistors or MOSFETs that are obviously doing some kind of slightly more advanced switching than the MCU just turning on the heater through the MOSFETs once the button is pushed. So this actually intrigued me, the complexity of these transistors, to reverse engineer this board and have a look at what kind of safety features and cross-checks the designers had put in. So I've drawn up this data sheet, this schematic, should I say. Just zoom out here a little bit to explain the functioning of this board. So just a quick orientation. I've laid the schematic out into functional components that very roughly correlate to the distribution on the board. So this is the MCU we have here, the linear low dropout regulator for the 5-volt board supplies here, the 2 large MOSFETs and the heater correspond to this here, and the connectors that were on here, I've just drawn those connections, the NTC and the LED, for example, into the schematic. So we can get this board out of the way for a second, and I'll go through explaining how the PCB works. So the first section we have here is the startup. So the way you use this machine, you plug your battery in, you push the only button it has, and it lights up an LED. So that switch that's present is on this connection here that goes directly to ground. So the moment you press this switch, you ground this point here, which is on this 20-volt rail going through this diode and through these resistors and then onto ground. So at the base of this PNP transistor, you pull it to a lower voltage than the 20 volts that it's usually at when this point here is just floating. So this transistor here, which is an NPN, controlled by the MCU at this point on starting is off. So the voltage at the base here is 20 volts from the battery rail. When we pull this switch, when we push this switch and pull it to ground, we activate this PNP. It actually goes through this 10K and 2K voltage divider. So we don't have ground at the base. We have 2/12 of 20 volts. So as to protect the base, since the emitter base limit threshold is probably only 5 volts. So if we were to pull it directly to ground, we'd damage the emitter base junction. So through this little voltage divider and of course the drop through the diode, the base on the transistor goes low, it's PNP, so it turns on, and it actually delivers the 20 volts from the battery to the 5-volt regulator. And this 5-volt regulator then directly powers the VCC pin on the MCU, and the computer itself wakes up and starts doing its business. But the issue we have here is when we release this button, the grounding to this point here disappears. So what the MCU does, it energizes pin 6 here that delivers positive voltage to the base of this NPN transistor and pulls this thing, this rail here, down to ground again. So you turn the machine off by a short grounding button press, and once the MCU receives its 5 volts operating power, it activates this NPN transistor, which again pulls it to ground and keeps this 5 volt circuit functioning. You can see here also that we have this diode and 4.7K resistor going to pin 3 of the MCU. That is actually used for on-switch detection when the machine is already operating. So when the machine is off, the MCU doesn't have 5 volts, it's dead in the water, it doesn't know what's going on. You push the switch and you activate anything, but you also have the function of turning off the machine or stopping a brewing process in mid-brew. So the MCU has to know when that switch is being pushed again. And the way it does it, it has this diode and resistor going to pin 3. I believe these are pulled up to its 5 volts operating voltage. So when the switch is pushed and the machine is operating, remember here we have 12 volts usually at this point. So when the switch is open, there's 12 volts in front of this diode and 5 volts from the pull-up of the MCU here, and nothing happens. But when the switch is depressed, this point here goes to ground, and the pull-up on this pin 3 before the 4.7K resistor, that goes from 5 volts here to some voltage under that, and the MCU can realize that this button is again being pushed. So the next function we have here is the indicator LED. That's very simple, just pin 4 of the MCU going down to this 500 ohm resistor to the green LED onto the ground rail. So the next function we have in line here is the temperature regulation or detection of the coffee machine heater. This is done quite simply. We have on pin, let me see here, pin 2, I believe, is where the NTC feed is connected. So pin 2 actually goes high to 5 volts when it's sensing the temperature, and then the 3K resistor and the 10K room temperature NTC make this voltage divider that is sensed onto pin 13, and it serves to measure the temperature of the heater. So if it overheats or if it's regulating a specific heating temperature it wants, as we'll see later through PWM modulation of the heater, it's going to get that temperature information through this voltage divider here that's sensing the voltage at this point here through this 1K resistor onto pin 13. You can see there's some protection here just with a capacitor to avoid any ripples and any kind of noise on that detection line. So the next function we have here that I'll just quickly explain is this D connection point. So that actually corresponds to the middle pin of our battery connector. So we have our positive and minus here, and then we have this pin here. And usually these Parkside batteries, they actually have 4 connectors on them. But you'll see the devices that use them only have 3 pins. So they connect to the positive and negative, but they also connect to one of the middle 2 pins. So in this case, this pin here connects to this connector here. And what these batteries actually have, I believe one of the pins is to an internal thermistor to detect the cell temperature, and the other contact goes to its MCU, and it's able to establish some kind of digital communication. So since those batteries don't have any internal switching, so there's no big MOSFET protecting the battery from under or over voltage, it's up to the consumer device to actually manage that battery. So here we have our connection to what I believe is the digital communication port, although it could also be the thermistor, I'm not 100% sure, that's sensed by 2 pins on the MCU, pin 12, going through the 1K resistor with its capacitor to ground for stability, and another 1K resistor to pin 8, all going to that same contact. So one thing I'll explain here is actually the voltage sensing that the coffee machine is doing of the battery. So the battery is of the Lidl 20 volt Team series. They have a microcontroller on the PCB. They have a single shot fuse, but they don't have any MOSFETs to actually cut power from the battery. So it's really up to the consumer device again to check for its voltage, unless it's getting that information communicated across this digital channel, or if this is the thermistor and it detects an overheat, it needs to cut the usage of the battery. So here, this voltage sense part we have here is connected to the 20 volt battery rail through this N-channel MOSFET, but it's not being detected all the time. So the gate of this N-channel MOSFET is pulled to ground to keep it off, and only when battery voltage interrogation is going on through this connection here onto pin 7 through a 1K resistor is the gate turned on. The battery rail voltage is able to pass through the N-channel MOSFET, again through a voltage divider consisting of a 50K resistor and this parallel array of 5.6K resistors. So this is 2.8Ks. So that voltage divider is sensed here, again by a 1K resistor going all the way back to pin 9 for voltage sensing, and again has noise suppression with a capacitor to ground. So the main function of the coffee machine, of course, is to heat this heater and make coffee. So the way the system is configured, and it's very sort of safety conscious, I'd say, is that it's using an arrangement where it can very precisely control the gate drive to the 2 parallel big MOSFETs N-channel that power the heater. So the starting cascade of the heater starts off from pin 5. That pin 5, when it wants to turn on the heater, goes high. It takes this NPN transistor, its base goes high, which connects the collector to ground. And this collector here goes on to a P-channel MOSFET over here, and that activates it when it's pulled to ground. Again, the gate of this P-channel is held at 20 volts battery voltage through this 4.7K resistor, so that's held usually off until pin 5 fires, activates this transistor and pulls that gate towards ground, again through a voltage divider, so that the gate again is not as stressed being pulled all the way to ground. Since this is a 20 volt rail we're dealing with, it is then pulled to some lower voltage. So this gate here is turned on. That is connecting the 20 volt rail, which is able to pass through the P-channel MOSFET. It goes through this 3.9 volt Zener diode, through this 51 ohm resistor, and it's able to pass to the gate of the big N-channel MOSFETs here to drive this heater through this small 5 milliohm voltage sense resistor that we'll see in just a second, through the MOSFETs and to heat the resistor. But as we can see here, we have a little bit more complexity on that gate drive. So it doesn't just stop here with the positive voltage going to the gate drive. We also have this complex of MOSFET and transistor. So what we can see here actually is that this N-channel MOSFET is connected to the constant 5-volt rail and is constantly held powered in heater off state. So this MOSFET is going straight to ground, so it's actually pulling through this 20 ohm resistor. It's pulling the gate drive circuit to ground. So even if this side was providing voltage, we'd have it be pulled towards ground here, and this gate would not be able to activate. So here we have this so-called push-pull configuration where the two MOSFETs that power the gate drive operate in opposite pairs. So when this one is on, this one is off, and vice versa. So we can see when the heater is wanted to be in an off state, this is conducting the ground connection to the gate. But in the case that we want to activate those heaters, we want to present our voltage to the gate and remove this grounding connection here. So the way this is done is through this NPN transistor, which if we can trace its drive back a little bit, it's slightly convoluted in my drawing here, but again it goes to pin 5, which is the heater activation pin. So it is pulled high, NPN transistors turns on, and it actually takes the gate of this N-channel MOSFET to ground. So this N-channel MOSFET is disabled, and since pin 5 again activated this N-channel MOSFET that activated the P-channel that is providing our gate drive of some 16-17 volts and activating the heater. So here we have this push-pull configuration. When the heater is on, this MOSFET is activated, this one is deactivated. We have positive drive to the MOSFET. When the heater is turned off, this MOSFET is deactivated, this MOSFET is activated, the gates are securely grounded, and there's no way for that heater to be activated by accident. As you can see here, again, in a normal state of operations, this base is pulled to ground through this 47K resistor, so it is off. The positive 5 volts that are on this rail are holding our N-channel MOSFET activated, and the gate is securely grounded. So we can see that we have a couple more diodes across our heating system here that are there for reverse polarity protection. So we can see here we have a direct diode connecting our ground to 20 volt rail. So imagine if we put the battery in the wrong way, we'd have ground here, positive here. That diode would make a short circuit and hopefully either blow a fuse or stop the battery output. But we have a big problem that if we didn't have good reverse polarity protection, our heater would actually be activated when we plug the battery in the wrong way without any electrical control. So if you manage this rail were to become ground and this were positive, you'd flow through your current sense resistor, you'd flow through the body diodes of these two big MOSFETs, and you'd flow through the heater, and you'd be heating without any control, and you'd have a runaway thermal event that could start a fire or injure someone or whatever. So what they've done here, they've provided 2 more diodes to protect in this situation. So even though these two MOSFETs have built-in body diodes that I haven't shown here, there's another diode connecting the source to drain additionally. So basically, there's pretty much 3 parallel diodes pointing towards the positive rail here, and then there's this one very big diode bridging the heater towards the positive rail. In a case of reverse polarity, your current would go through the current sense resistor, it would pass through the body diodes, but instead of passing through the heater, it's provided a lower resistance path through this big SS54 diode here to our newly minted, wrongly connected ground, and that stops the heater from heating when the reverse polarity is connected, and in those few instances of high current conduction, it is expected that the fuse will stop the device from working. So you can actually see the fairly large size of these diodes that they've used. So this SS54 corresponds to this diode across the heater here. This diode directly between ground and 20 volts is this smaller MCC diode here. And then the diode going across source to drain is this diode up here. So that's pretty much the functioning of this device. The only thing that's left is this current sense resistor, 5 milliohms, that is connected up to pin 10 here through this 1K resistor and with a noise decoupling capacitor here. So anytime the heater is in operation, there will be a small voltage drop across this current sense resistor, which is actually two 10 milliohm resistors connected here, and that will tell the computer that the heater is actually functioning. So in the case of, let's say, a burnt out heater where the device would try and activate the heater but there's no connection, this current sense resistor would tell the MCU that there's a problem with the heater, and it would shut it down and possibly flash some kind of error code. So in testing of this machine, I've noticed that it obviously won't want to operate with no heater installed. So when I connect this board itself to a battery, just like this, which is quite handy for testing, and connect a button to here, and the NTC thermistor here, it won't actually operate the heater for more than a second since it's not connected, and that current sense resistor isn't showing it any voltage or current passing through the heater. Also, it won't run without the NTC thermistor, so again, these are all safety things. If the heater's broken, it knows there's a fault, it doesn't run. If it's unable to determine the temperature, it also doesn't run. One interesting thing on startup, it actually does a kind of soft start on the heater. So it starts with some pulse width modulation with a very low duty cycle, and it slowly ramps that up. And I haven't done too extensive testing on it, but it seems to me that it does try and hit a target temperature with the heater, so it does apply pulse width modulation in reference to the temperature it's measuring over the NTC in order to regulate the temperature of the circuit. And since we just have that gravity-fed heater in this system, so the water tank is just gravity feeding water sitting in this U-bend, and when the heater activates, steam comes out the other end and into your cup. Some type of temperature control obviously is of incredible importance. So here are just a couple of things. I've drawn out the different transistors and MOSFETs that are used with their short SMD markings, so you can see them here. The MOSFETs that are being used here are 30H10K model number. Those are 100 amp, I believe somewhere around 2 milliohm RDS on 30 volt MOSFETs. So in this application here, even though we are not using the full 100 amp capability of each, we're using 42 amps at best, probably for thermal and heat sinking reasons. Even though we're doing non-continuous pulse width modulation, they've actually split the power across two of the MOSFETs just to allow that better heat dissipation and to cut down on the overheating of those MOSFETs. So that's pretty much it. It's always interesting reverse engineering these simple household devices that one comes across time and time again, and just looking at what the engineers have done, what kind of safety features and what kind of tricks they've hidden in their designs. And this to me seems like quite a comprehensive control system where it's monitoring both current and temperature and using this push-pull MOSFET configuration on the gate drive to ensure a fast and hard turn on, which is important using MOSFETs in high current operation, and of course a very hard and fast turn off, grounding those gates, because you do not want these MOSFETs that are conducting up to 42 amps going through their linear conduction phase, which would cause the RDS on to go quite high, and that's when you actually blow a MOSFET. So when you're doing high current conduction with a MOSFET, you want it to go hard on, take the gate right up to its almost maximum gate voltage, have it in its lowest RDS on state so it can conduct, and when you're turning the device off, you want to pull that gate down to ground as quickly as possible. Here they're pulling it through a 20 ohm resistor, so very low impedance, straight to ground when you want to turn it off, to ensure that the MOSFETs don't go through that linear phase where they show high resistance to the load, and where they would thermally blow up within milliseconds if they were slowly bled of their gate voltage. So that's pretty much that on this topic. Interesting little coffee machine, interesting and fun circuit to reverse engineer. Nothing too hard. You can stick your flashlight, even though there is this fairly large ground plane, and you can map it out. Obviously some vias that are a bit annoying to trace out, but otherwise fairly robust and quality built product. Thanks again for watching, and see you next time.